Hello, this is Lab 4, Bar Magnets by Bryant Gossett. So the purpose of this lab is to measure the dependence of magnetic field on the distance of a small part magnet. We also compared the predicted and observed values for both on-axis and off-axis magnetic fields. So a little preview, we calculated dipole moment mu, 5.0653 amperes per meter squared, and slope of negative 1.99. So here's our calculation. I just did it on an iPad. Physics principles of the magnetic field of a dipole basically describes how magnetic fields decrease cubically with distance and model how the fields loop from north to south, just like the electric dipole loops from positive to negative. Yeah, and it's kind of like a dipole, except in magnetic fields have no like beginning or end, and electric fields definitely have beginning or ends. So yeah, and then we use perpendicular and parallel, but we use the more accurate, I guess, dipole moment as like calculated in the physics slide. Picture the experiment. Here we go. There's a phone. Oriented the phone's magnetometer so that it's orthogonal to the field. And then got the location of it through the little calibration process with the tape. And so we got as accurate results as possible. We measured the distance between that center of the magnetometer and bar magnet. Here's the results. So we predicted it was, at the distance, 0.11 meters. We predicted 7.6 times 10 to the negative 4, but actually 2.2 times 10 to the negative 4, which is, not that much different. So, it's not really that big of a deal. And then for perpendicular, at distance 0.187, we calculated 1.37 for x direction and 4.11 for the z direction. And then it was really 9 times 10 to the negative 6 and 2.2 times 10 to the negative 5, or negative for both of them. And those are very close to the actual numbers we calculated and close to the model. And it's really just got to do with the orientation of the phone magnet. If you flip them around, it's going to be different. It's going to be positive. We set dperp to 0.187 and mu to 5.0653 because the previous calculations. We went from there, made several arrows, which you'll see below. So here are our results, and it just goes through some code. You can look at it. I don't know if you can see, but there's a little tiny arrows in the top and bottom. Those are those magnetic fields at distance 2D. I set D as 0.11 for this, and then I set the D perp to 0.187. So D, the one with all those arrows, is 0.11. Yeah, we're assuming there's no other current besides the magnetic, and therefore magnetic fields that interview with that experiment besides Earth's, that we have exact measurements. Our magnetometer is accurate. I forgot to say, we forget that it's the equation for that magnetic field is also, I believe, a bit of an approximation. So the equation, might just not be accurate. We also assume there's no human error. We could have made a calculation mistake, we could have made a coding mistake, we could have made something. We don't know. And then our results are that magnetic field can be measured to be larger or smaller than it is. But this is because of cancellation of fields or addition or subtraction of those currents. Because if they're in certain directions, they'll add. If they're in certain directions, they'll subtract. And that's, very different. So yeah. All right, magnetometer, I'll just go through all these. I'll say that the first question is true. Yes, very far away, R goes to infinity, so that limit goes to 0. False, it increases. False, it increases or decreases based on distance. And true, because it increases as you move closer. Not compensated, it would interfere with the magnetometer, and we wouldn't be able to cancel that out. We canceled out the magnetic field from Earth. And the other one, magnitude would be double, direction would be the same. Yeah, basically the magnetic dipole moment doubles, and it's 2 times that. So yeah, thank you so much.